Hi, for the task allocation, Shavina are going to explain about the introduction and objective. Second, Hairudin will be explain about the problem solving. Ashraf about the entities explanation, and last one is Zahin for the conclusion. Kinematics is the study of motion without any reference to the forces that cause the motion. It basically means studying how things are moving, not why they are moving. It includes concepts such as distance or displacement, speed or velocity, and acceleration, and it looks at how those values vary over time. Objective: to illustrate the velocity variation in an open pipe flow with 300 mm length and diameter at 60 mm.
For the problem solving, first for the problem is the velocity of the water inlet is 0.005 meter per second and the diameter of the pipe 30 mm and the length is 300 mm. So we need to find the velocity variation of the pipe. The solution is find the volume rate of the water entering pipe. The volume flow rate can be calculated by using formula Q equal to A times V, where A is cross-sectional area of the pipe and V is the velocity in the water. Next, the cross-sectional area of the pipe can be calculated by using formula A equal to pi times D over 2 power of 2, and D is the diameter of the pipe. And for the step 3, calculate the volume flow rate at the given formula, and we will get the final answer 0.157 power of 10 negative 6 meter cube per second. And for the next, since the pipe has a constant diameter and there are no external force acting on the water, the velocity of the water will remain constant throughout the pipe. This is due to the principle of the conservation of mass, which states that the mass flow rate must remain constant in a closed system. Therefore, we can conclude that velocity variation in the pipe is 0 meter per second.
For this part of this video, I am going to elaborate on the steps needed to solve the problem given. Click on Fluid Flow Toolbox. Then, click on Geometry and you'll be able to see a properties table. And choose 2D as we are going to do a 2D analysis. Then, right click on the geometry and select New Design Modeler Boundary to create the geometry. Set the default unit to mm. Select the XY plane, click on Z plane to make the sketch normal to the screen. Switch to Sketching tab and select Rectangle from the Draw toolbox. Sketch a rectangle and set a dimension of 300 mm length and 30 mm width. After the sketch is complete, go to Concept menu and click on Surface. From Sketches to convert the sketch into 2D geometry. Click Generate. Click on the surface body from the tree outline and change the body type to fluid so the meshing surface will mesh it as fluid domain. Change to fluid. Click Generate. Exit the design modeler. For a meshing process, open the meshing workbench window. Generate the mesh using default mesh setting. Check aspect ratio by select display style and detail of mesh. To further decrease the mesh size, we have to modify it. Change the element size for 1 mm. Regenerate the mesh. The minimum aspect ratio for this geometry is 1 and the maximum is 1.0111. The nodes number are 9331 and element are 9000. For naming a boundary, find selection tools and choose edge selection. Right click on the edge of the geometry and select create name selection. All the name boundaries are listed in the tree outline. Under name selection, it might cause an error if it named twice. Double click on the mesh by right click on the mesh and select update. A message will appear when mesh transition is successful. Recheck the naming selection. All the name boundaries are listed in the tree outline. Under name selection, it might cause an error if it named twice. Close the machine. Click on setup and select edit. A fluid launcher window will appear. It will ask regarding whether you want to set single or double precision. Select double. Single precision will only take a short time to solve, while double precision will take much longer with a more accurate result. At the analysis fluent window, we will boundary condition and do necessary setup. For 2D space, choose asymmetry as we are doing an asymmetry analysis. Check the loaded mesh analysis. Select the required flow model from the list. For viscose model, choose Lamina as the current problem is 9.952, which is less than the Reynolds number of 2300 for 5 flow case. Load fluid material from fluid database. You could also change the material properties as per your requirement for this simulation. Choose water for fluid material. By default, the solid material will be aluminium. Now, assign the material to the fluid domain mesh body. Click the operation condition tab and put the pressure of atmospheric pressure. Then, switch to boundary condition and put the required boundary. As per name selection, the solver assign the boundary condition type by itself. You can change it. Select velocity inlet boundary condition of the inlet and put the inlet velocity of 0.005 meter per second. Keep the default pressure outlet boundary type for the outlet boundary. No need to change the default pipe wall as the pipe is a stationary one. Go to solution method and select simple in the pressure velocity coupling scheme. This will define as the implicit method for pressure linked equation. Then go for monitors and select residual and decrease the residual to -6 for a better solution accuracy. The iteration process can be continued until all the numerical iteration achieve this residual value. Next, click on initialization and select the standard initialization. Select compute from any boundary, then press initialize to finish the solver setup process. Click on run calculation and set the number of interaction at 1000 to run and start the interaction process by clicking on calculate. Calculation is complete now because all the numerical equation reach the residual value of -6. Check the result. See the variation of velocity as the form of a contour. It can be seen that the velocity is maximum at near the central axis and decrease toward the pipe wall. Check the contour for pressure. Check the velocity variation along the external axis. Go to plot. Select XY plot. Choose velocity for Y axis and select axis for X axis. Click on plot. Now, close the machine and proceed for CFD post-processing. Double-click on result to open CFD post-processing. Insert a contour to observe the velocity variation. We could also create the contour for the full pipe body. This donate the color bands for the contour. For more number of color bands, increase the number of color bands. Change the number and click apply. We could also change the default legend view. Change the precision to control decimal place of velocity. Apply reflection to show the contour of a full pipe body. Click on view, enable apply reflection, change the method to ZX plane, right click on contour and click duplicate. Choose the location on periodic 1, click apply. Create the velocity vector for the domain. Create the reflection to see the velocity vector of a full pipe domain. Change the method to ZX plane. Right click on contour and click duplicate. Click on view, enable apply reflection. Change the method to ZX plane. Right click on contour and click duplicate. Check the streamline. Choose inlet on start from. Create the reflection to see the streamline of a full pipe domain. Click on view, enable apply reflection, change the method to ZX plane, right click on contour and click duplicate. Animate the flow in this pipe domain using quick animation option. You could also modify symbol size and spacing. Save the animation by choose the file save location. Click on the chart to insert a chart velocity variation graph. In the details of chart, switch to the data series tab. Select the line as the location. For x-axis, choose variable x. For y-axis, choose velocity. Select y on x-axis to see the radial variation of velocity. With this, we conclude this demonstration.
At the end of this CFD simulation project, we are able to hands-on directly using this Workbench software, and also can compare the final result from our theoretical calculation. In addition, we successfully met our objective clearly. That's all from us. Thank you.